Today we're going to look at equilibrium of a rigid body. Two parts. First part, we'll have to think about the conditions for a rigid body to be in equilibrium. And the second piece of this is coming up with the free body diagrams. Okay, so first we'll start with looking at some applications. Okay, so here's an application. You have a ramp and it's pinned to the body of a truck and held in position by the cable. All right. Now, there are a couple of things here, we have to think about. We have to think about, the equilibrium condition being that all the forces have to sum to zero and all the moments about any point have to sum to zero too. So if you're looking for, like a case like this is really can be approximated two-dimensionally, you're going to have forces, and if you look over to the right, if you came up with all the forces that are involved in a diagram of that, a free body diagram, you'd have a force of tension on the cables. And this is what, from the ramp's perspective, you have the weight, which you can actually put that at the center of gravity or the center of mass of this object. And then you have another thing here, which is we're starting to look at now, is this idea of a reaction. Okay. So if there's an overall force, like in this direction, what would you come up with? You would come up with a tension in the x direction, which would have to be equalized or canceled out by a reaction force, because this is the only place that's connected to the truck, in the opposite direction, the x direction. And the same thing goes for the y component. So you have a y component here, and you have gravity acting downward, and you have a reaction at this pin, which will add to zero. Okay? So the first part of this is that in order for this thing to be in equilibrium, you have to sum, if you sum all the forces, the forces all have to equal to zero. The second part of this is that any reactions, second part of this is any reactive or any moments have to be canceled out by reactive moments. Okay? Now, if we look at this kind of a support here, this thing is at where it's connected to the truck. It's actually free to pivot around this. So this support, where this is actually connected, does nothing to stop rotation. Okay. So what you're going to end up finding is that you can do like a moment equation about this point A. And what you're going to find is that you have potentially you have an x, and the x is canceled out here, but you'll have a component in the y direction here, which makes a moment that would cause clockwise rotation about this point. And then you have something due to t. And in this case, you look at, well, you could have an x component and draw it straight on through here, and you have a distance from here up to that point, and that will give you rotation in the same direction. And then you have a y component, that'll give you rotation in the other direction, or about the, that would be in the clockwise direction. The other one was counterclockwise. And you have an x component do that, so it's from here to that distance if you draw the line straight through. And then you have a y component due to this t also, which is acting down, which is acting in the other direction. So you can come up with moment equations also. So in this case, if you look at this particular problem, what would you have? Well, when you started off, you would know the weight, but you wouldn't know the tension, and you wouldn't know these reactions here. But if you think about it, so you have three unknowns, the tension and these two reactions, and we could come up with three equations two-dimensionally. We can come up with a summation of the forces in the x direction and a summation of the forces in the y direction, and those all have to sum to zero. And we also have moments about any point on this. You could draw a moment, you could create a moment, you could actually do it about g if you wanted to. But the moment's about any point, and if we choose A, that also has to sum to zero. So now we have three independent equations and three unknowns, t, ax, and ay, and we could solve for those. Okay? All right. So we use the free body diagram, and the idealized is like this one. The free body diagram tells us in terms of like the actual forces that are involved in the positions of those forces. Okay. All right. The next thing, here's another problem here, and it's the same idea. It's in equilibrium, right? You would hope that these things aren't rolling off. They're just going to be sitting there resting in here. So if you think about it, you would have forces. You'd have the normal forces. You have a force, force in this direction acting against this. You'd have another one acting against this, normal to that. And then you have a force that this is pushing on that one, on this other pipe. And then you have a normal force here. And then you have the weights of these two pressing down. Okay. So you could go through the same kind of problem where you have, reaction here, reactive force here, and a reaction here. Okay. And in this case, they combined the two. They didn't really consider the reaction of these two. They just had it where these two together are connected to the forklift, or the fork on the lift. Okay. So here they just drew, here's a reaction, here's a reaction, and here's a reaction. And then you have the forces acting straight down. So in this case, you could break it up into the X and Y components and come up with reactions there too. Okay. Okay. So now we can think about this like in 3 dimensions. Okay. So here are our equations, right? Our equations for equilibrium. So we just think about generally if force is on a particle. There's no translation if the summation of all the forces is equal to 0. And there's no rotation if the summation of the moments about any point, in this case you could just pick point O, if that's also 0. Okay. So for those first two problems, or the first two applications that we were looking at, we want to make sure both of those are true. Okay. So you have reactions. This could be considered a support for this. So this the supporting these two pipes actually provides a reaction on those pipes so that they stay in equilibrium. Okay. All right. Okay. So going back to coming up with the idealized model. So this one is just that, drawing the model as it is. And then typically, we would go straight into our free body diagram, not necessarily drawing the idealized model, as long as we had this information given. Okay. So here, free body diagram has to include these reactions, right? In the past, we did moments about a point, or moments about a point due to some couples and some forces acting at some distances. But now we're going to take a look at the whole system as a whole and make sure that it's in equilibrium. Okay. And one of the things, in this case, what would we care about potentially? Well, we want to make sure that this cable is strong enough, right? The tension in this cable is strong enough. And these pins are strong enough to hold whatever forces are acting against them too. Since there's no rotation about the pins because is it a pin support and it doesn't provide any reaction to it, these are the only two things we need to add here. So these are the additional parts of our free body diagram that we have to add for equilibrium. Okay. All right, so here's one. Here's a free body. We're going to look at a free body diagram for this particular problem. Okay. So here's the idealized model. This is the model of the system. We have a bar. We can assume that this cross member, this I-beam, doesn't have any mass associated with it, or it's weightless, or it's relatively small compared to the actual force acting here. And it's connected in one place. Now, if you this is a fixed support, so this one doesn't actually provide any reaction. This does not allow any rotation about this point. It definitely provides reaction. And if you think about it, if you tried to push this bar up or pull it down over here, this is going to resist any kind of rotation. If you push with enough force or pull with enough force, push up or push down with enough force, you could actually cause this thing to potentially rip out of the wall. Okay. But for this type of support, when we go and analyze it, there's a few things here. If you try to push it in, it's going to resist pushing in. So there's a reaction over here in the X direction. And if you try to push it down, straight down, there's another reaction that would be pushing back up, equal opposite force in the opposite direction here. Pushing back up, a reaction pushing back up of the same magnitude of whatever's pushing down. And then you also have a reactive moment. So this thing is trying to cause clockwise rotation about this point, this force. So you would draw on a reaction, essentially, that's in the other direction. That's in a counterclockwise direction. Okay. Now, one of the things about when you actually go and draw your reactions, and here's the reactive moment, here's the reactive force AY and reactive force AX. is that if it comes out when you go and solve for these reactions and they actually come out to be negative, all it really tells you is that, oh, you drew it in the wrong direction. The reaction is actually in the wrong direction. If the moment is negative, what it's telling you is that the reactive moment is just in the opposite direction, okay? So in this case, if you look at it, you say, well, okay, I know this force. Oh, sorry, this is not this is not massless. It actually it's 981 newtons, the gravity of this beam, so you have to include that in the equation, although I didn't say that over here. You have to include the weight of this at the center of gravity or center of mass, and then the force here, okay? So for this particular problem, there is a mass associated with this I-beam. All right, so what we would do is we would draw the free body diagram. We have to include these reactions, okay? Now, this different than the previous one in terms of the pin, the support, how it was connected to the truck. It was on a pin. This one is actually a fixed support, so it actually has a reaction to stop this thing from rotating. And like I said, you can draw this, generally what we do is we draw this in the counterclockwise direction so that we have it as positive. So it makes it easier to keep track of. That way, in the end, if MA comes out to be negative, then we know, oh, it's really just in the clockwise direction, okay? All right. So here's our free body diagram with all the forces and reactions defined here, okay? All right. Okay. So draw the outline shape. Okay, this is all the free body diagram. Then show the external forces and the couple moments. Okay. So if we had any other couples in here, we would add those. We only have this couple moment here, the reaction. Okay. Okay. All right. So the next thing you would do is label the loads and dimensions on the free body diagram. All right. So this is critical, of course, because you got to come up with an accurate free body diagram. If you don't come up with an accurate free body diagram, then, of course, if you neglect to put a reaction or a force in there, you're going to come up with something that's not correct. Okay. All right. So this leads us to the next part. So this is just coming up with free body diagrams for these particular problems. The next part is thinking about the types of supports. So how is this, your object, connected to the outside world? And these are the different types of supports with the different types of reactions, okay? Now, we can think about it in terms of a couple things, can this thing roll by itself? Can it move? And in this case, you can see, yeah, this thing could slide up and down this ramp, and it can also rotate. So this beam can rotate around this point, so it can also rotate. So there's nothing with this support, this is a roller support, that's going to stop this thing from sliding up or down or rotating, okay? The only reaction we have is a normal force pushing straight up. So here is how you would actually draw the reactions. You'd have some force that's normal to the surface that this thing is riding on, in the opposite direction, acting right on that pin, okay? The second type of support we're going to look at here is a pin support, and that's actually like the truck support, right? It's fixed, so there's reactions there's reactions stopping it from this bar from pulling up or pushing down or going off to the right or the left, but it can rotate. It's free to rotate. So while there are two reactive forces here, there's no reactive moment, okay? Now, this is a fixed support. This one here now has a reactive moment. That was the second problem we looked at, right? So now you have a reactive force in the x direction, a reactive force in the y direction, and a reactive moment. In that case, in the clockwise or counterclockwise direction. We'll draw them in the clockwise, so we keep counterclockwise, so we keep it positive, and that will be at that point. Okay. So those are our basic, for 2 dimensions, here's our basic types of supports, okay? And the first types of problems we'll look at will be in 2 dimensions. Okay. So you just got to think about, support prevents translation. Translation meaning, moving in one direction or another. Force typically is going to be the opposite of that reaction, right? All right. And okay. Rotation to prevent a couple moments exerted on the body in the opposite direction. Okay. Well, that's just kind of what we had talked about, right? It's basically opposing motion, either rotation or translation. Okay. Depending upon the type of support it is. Okay. So here's another problem here. Okay. So what we want to do in this crop, and you know, at this point, we're not going through and doing any math. We're just trying to come up with free body diagrams that represent this system. Okay. So our first thing here is we can look at this one and say, oh yeah, this looks like this is a pin here. You know, you have some force acting on this pedal, and it's going. You have some spring force pulling in this direction, and then this one, you know, this bar is moving off to the right or the left on a pin support. Okay. So let's look at the idealized model and the free body diagram. Okay. So, okay. Oh, so at this point in time, we're applying the operator's applying a vertical force, so pushing straight down. So here's the idealized model, which basically shows everything: the dimensions, the distances, the actual objects that are connected, okay, and the distances or the displacements between them, okay. And here gives the information on that particular spring. Okay. So the free body diagram, and you can actually, if you think about this one, it's actually telling you how far that spring is stretched. So we can actually replace this with a force. Okay. And the force on the short link B is 20 pounds. Okay. So we already know what this one is. You know, he's pushing down. There's a force, in this case, trying to pull off in the opposite in this direction. And then the spring, of course, is resisting it too. It's in the opposite direction. And then we have some reactions, okay? So point A is really where this thing is connected. So if we look back, of course, we see our support. Here it is. Here's our pin support, right? So our pin support does not stop, of course, rotation. It does not have any reaction to stop rotation, okay? All right. So free body diagram, of course, is just going to have a force acting straight down at that position, and then the two reactions, and then the forces here. So we have two reactions, only two reactions. So if you think about it, you're like, oh yes, they really only need two equations: summation of the forces in the x direction and summation of the forces in the y direction. And you can think about it and looking at this and saying, oh yeah, whatever force he's pushing down, it's going to have an equal and opposite reaction pushing back up. And then we have 20 and 30 here, and AX is just going to oppose those two. So there's a force here, a reaction at the pin in the x direction equal to 50 pounds. Okay? So relatively easy, but you have to think about, you know, how do you draw the difference between this and what we did before is how do you draw the reactions. Okay. All right, second example. All right. The second example here, okay, you have a platform suspended off the edge of an oil rig, has a mass of 200 kilograms. We want to get the idealized model and the free body diagram of the platform. Okay, so we're going to look at this in two dimensions. All right. Okay, so one of the assumptions we made is we'll make for this particular problem is that we can draw it in two dimensions because we're going to consider everything to be symmetrical about a vertical plane passing through its center, okay? Because we have a cable here and a cable here, okay? All right. All right, so here's the idealized model, right? So we have some, and you can look here and see what kind of, you know, we have this connected. This is just a pin or whatever. But really, you know, what do we care about? Where this thing is actually connected. Here's a pin support here. Here's a cable. So as far as how this thing is connected to the platform, we have just at point A and a tension along this direction connected to another point. So these are the 2 points. So these are the two reactions essentially, or tensions you want to think. Here's a reaction at point. Here's a reaction for a cable. Okay. And then we have the mass acting straight down. All right. So what we're going to see here, we draw the reactions. We have an AX and an AY. And then we have some tension. So if you think about it, it's like, well, this one is only acting in the Y direction, and then, or the negative Y direction. And then we have a component here in the positive Y direction. And then we have another one in the positive Y direction. So we would sum this force, the reaction, and the tension here, the Y component of the tension, and that would give us our summation of the forces in the Y direction equal to 0. And then in the x direction, we're going to have basically a force acting in the positive x direction subtracted from the x component of the tension, which is just t cosine of 70 degrees. And that will give us, we sum those, set it equal to 0, and that will give us equations in the x direction. Okay. Okay. Okay, so here's another one. All right, so if we look at this one, you have to think about where this thing is actually making contact. Okay. And if you think, you could see that this bar is just sort of resting on here, so it could probably slide back and forth. And maybe it's just kind of pivoting on this point. And same thing here, and same thing here, okay? So if you really think about it, you're going to have some force. Okay, I can break this one up to x and y components here. And then this one is basically horizontal, so you could have a y reaction right here. And then we have another one over here acting down. And then we have one here acting off along this surface, okay? So acting in this direction, right? So first part, we think we're going to have a reaction at A, or reactions potentially. We're going to have reaction at A, B, and C where this thing contacts. Okay? Okay, there's our idealized model, which is just essentially what we were looking at. And here's the reactions. Okay, so we see B is going straight down, C is going up, and then A is off on an angle defined by this 30 degrees because it was shifted by 30 degrees down. Okay, so here are our reactions, right? Now, if you think about it, you say, well, what do we have? I'm going to have some y component here. So that's a negative cosine of 30 times 300 newtons. And then we have a reaction in this direction, positive y, reaction here. And then we have another reaction here in the y direction also, which is the sine of 30 times NA. Okay? And we could do the same thing with the x direction. We have the sine of 30 times 300 newtons, which is this component essentially. And that would cancel out the x component here, which would just be the cosine of 30 times NA. So it wouldn't be too hard to find out what NA is from that equation. But in the y direction, we're going to find we have 1, 2, we still have 2 unknowns, and we have the y component here. So we'd have to figure out what these are. Well, so far when we looked at reactions and came up with equations, what we said was just the summation of the forces in the x direction equal to 0 and the summation of the forces in the y direction equal to 0. Now what we can consider is also the moments about any point. Okay. Now you can pick any point here, you could pick a point here, you could pick C, you could pick B, you pick A, any of those, and then come up sum the moments about that point and come up with an equation and set it equal to 0. Well, for us, we probably, the best thing to do in this case would be to think about it in terms of, should we do it about C maybe or B? We probably should do it about one of these unknowns. That way, if we did it about, let's say, NC, there's nothing that this point here would give us in terms of a moment. I'm sorry, there's nothing that this one gives us here at this point in terms of a moment. So in the moment equation, if I do it about point C, this one basically goes away. Then what we end up having is we're going to have the component here, the y component times this distance, which is 0.65. And that's going in, it'd be negative because it's going in the counterclockwise direction. And then I have the x component here, which is 0.26 up, and that's also in the clockwise direction, about point C. It would cause rotation in the clockwise direction about point C. And that one is just, the x component of NA at 0.26. So that's also a negative one. So we've got the y component, the x component contribution to the moment about this point. And then we have NB. And NB is, of course, just acting straight down. And it's going to be times 0.5 meters. And that's going to be 0.5 meters times NB, and it's going to be negative because in this case, what this one is it's going to cause clockwise rotation about NC. And then for the last part, We can think about this one breaking it up into its X and Y components, but what we'll see is that the X component, really just draw it straight along this line. It's not acting at any distance from this point. If you draw the line of action of the X component here, that doesn't contribute to the moment at all. Only the Y component. So if you do the Y component, 300 newtons times the cosine of 30 degrees times 0.5 meters, that is in the counterclockwise direction, okay, or rotation about this point in the counterclockwise direction. So this, the Y component of this guy, of this 300 newtons times 0.5, that's going to cause counterclockwise rotation, which is going to be canceled out by this one and the X and Y, this one times 0.5, and the X and Y components of this, of NA, times their respective distances, 0.65 for the Y component from here to here, and 0.26 for the X component, which would, if you drew the line of action of it, it would meet at 90 degrees with the moment at 0.26 meters here. Okay, so those would cancel out. So in this case, you need that third, you need the third equation to do that. Okay, all right. So we have one more to look at here. Okay, now this one you have to think about too is like how this thing meets and what kind of reaction it provides here. This one can slide up and down, but then it can't like push into it. So we'll have a reaction in this case straight here at point A. We have a force here. We have a moment, or sorry, a couple. Now the couple, even though they show it about this point, it doesn't matter anywhere. And if you come up with any equation about this, any equation, moment equation, this couple would be added to that equation. Doesn't matter what point, right? Because a couple causes rotation anywhere along this object, all right? And then we have another reaction right here, okay? So if we go through and draw those, okay? Here's our idealized model, which we already looked at. And here's the reactions. So you have one here that's acting straight. It's normal to this bar, okay? And the angles, of course, can be found from here. And then we have the force, the 100-pound force. And in this case, the assumption is that this bar is massless, okay? And then we have a reaction at B that's basically normal to this surface where it connects, okay? So now what you can see is we have an unknown here and an unknown here. And we have to include, you know, if we think about in terms of the rotation, we have a rotation that we have to include here. And we can break it up into our X and Y components. And we'll have to actually come up with a second equation that has the moments too, okay? We'll have to come up with a moment equation also and set it equal to 0 to make this work out. Okay. All right. And this one here is just one more thing. Let's see. Okay. So a couple more things. So the truck ramp has a certain weight associated. We can go, and it's pinned at A and held position by cables. How can we determine the forces acting pin and the forces in the cable? Okay. So that's what we had looked at previously. We looked at that application. Like I said, we're going to have reactions here and 10 tensions here. So since we have essentially 3 unknowns, we have to come up with 3 equations. And it would be the summation of the forces in the X direction, summation of the forces in the Y direction, and those have to equal to 0. And also, summation of the moments about point A also has to be 0. Okay? So the only thing, the forces that we would show in here is that, of course, we'd have our reactions here, and we would have, you know, the weight acting down at the center, halfway between here and here at this point. Okay? All right. Here's another one, another application. So in this case, and this one's just showing it in 2 dimensions. Okay? So this one here, what would we'd do the same kind of thing, right? We would make sure that, try to figure out what the tension in these cables are, just to make sure that they don't break or can support the weight of this engine, okay? And you do the same kind of thing. So you would see, oh, okay, I don't know what this one is. I don't know what this one is. So I have 1, 2, 3 potentially potential unknowns, right? Tensions in each of these cables. Okay. And so we would have to do the same kind of thing. So we would find that all of these have angles on them associated with them, right? And we would have if you think about it, we actually have X and Y tensions here, X and Y tensions here, and X and Y tensions here. Okay. So we need to do a couple of things. One is we'd have to come up with an equation for the forces in the y direction, and they have to sum to zero. Or you can think about it, oh, okay, this 850 has got to equal to the y component of this one plus this one plus this one, right? Because they're just acting in the opposite direction. And then the x components, it'd be like an x component equation has an x. This has an x tension associated with it. This one has an x tension associated with it. And this one has an x tension associated with it, okay? Now, in this case, you think, well, there's two equations. I actually am going to have three unknowns here. So we need to come up with another equation. And the other equation would be the moment equation. And however you can do it, you could actually do like, if we assume in this case, it looks like they didn't give us a dimension of this bar. So we assume this is, has zero height associated with it, this I-beam. And we could come up with an equation. We could do moment about A if we wanted to. We could do moment about B or moment about C. And what you would find then is if you did moment about, let's say, A, you'd have a moment due to the y component of this, a moment due from this point to this point here. We'd have a y component of this and the y component of this. Okay, so now you have another equation. In that equation, you would not know, what the y component of this one is or the y component of this. You'd have two unknowns. Okay, so your three equations would be summation of the forces in the x direction equal to 0, summation of the forces in the y direction equal to 0, and summation of moments about any point. In this case, I chose A, and that has to sum to 0. Okay, and then that, of course, with those three equations, we could actually go through and solve the tensions for each of these bars. Okay, and that's it for that part.